numbers with a fractional part. So we're looking at fixed point form and floating point form in binary, and the ability to convert between decimal or denary numbers and binary numbers using these forms. Now, fixed point form, as the name suggests, has a fixed point somewhere in the binary numbers. So in this case, we have an 8-bit binary number with the fixed point in between the 4th and 5th bit. What that does is it opens up the ability to represent fractional or numbers with a decimal part. So here we have 1 over 2, 1 over 4, 1 over 8, 1 over 16. That gives us access to these values. To the left, we still have our normal 1, 2, 4, 8, and so on place values. Now, if we were to fix the point in a different location, we would open up the ability to represent more fractional numbers. We would increase the precision, but that would be at the cost of the number of whole numbers that we can represent. If we were to fix the point over to the right, here we would have fewer numbers, decimal numbers or fractional numbers that we could represent, but that would open up the use of much more or many more whole numbers. Here we have a fixed point form binary number that represents the number 15.9375. To get there, all we need to do is add the 8, the 4, the 2 and the 1 together, and then the 1 over 2, 1 over 4 and 1 over 16. Add that all up and that gives you your number. Here's another. So we have 4 add 2 add 1, which gives us our 7, and then we're adding on the quarter, the 8th and the 16th, and that will give us 7.4375. Now there are 4 examples here for you to have a go at. If you want to pause the video, try these, and then I'll reveal the answer to you in just a second. So top left, top right. The bottom 2, you've noticed that I didn't provide you with the place values, but if you place them correctly, you should have these 2 values. Okay, moving on to floating point. So here we have a floating point number. This is a base 10 number, so not in binary. But the reason I put it on screen is that it kind of shows you that you may have already seen or used floating point numbers in your science lessons. So what we have is a floating point number 4.2 times 10 to the negative 4. This is a normalized representation of the original number. So this is packaged up in what we call a mantissa and an exponent. The mantissa is a representation of the original number before it was normalized. And the exponent essentially holds the information to get back the original number. So the exponent tells you what to do to the mantissa. So this number has been normalized. In base 10 for science, the general rule is that you should only have one non-zero significant figure before this decimal point. So whatever your number is, you package it up so it falls into this representation. Recorded in the exponent is what you did to get the original number into this representation. So normalized numbers include the instructions needed to unpack the number. Okay, the instructions are the exponent. So if we actually look at this exponent, we have the base number, which is where the times 10 comes from, and then we have negative 4, which is essentially telling us that we need to move the decimal floating point 4 places to the left. So if we actually do that, there's 1 place, there's 2, 3, 4 places. That is the original unnormalized number. So if we go back, this is the normalized number with the exponent telling us what to do to get back to the original. We go 1, 2, 3, 4 places, and there is the unpackaged or unnormalized number. So moving on to binary representations using floating point, we just need to remember that here we're using 2's complement. So we still have this same structure, the mantissa and the exponent. And in this case, we've used 8 bits for the mantissa and 4 bits for the exponent. Essentially, we have a 12-bit 2's complement floating point binary number. Now, in AQA exams, they actually tell you how many bits may have been used for the mantissa and the exponent. And just remember, throughout all of these examples, the decimal point will always be between the first two bits of the mantissa. So you'll notice that in the top right, I've put method 1. So I'm going to give you a few examples using. Here we have the first of two methods you can use to convert denary values into floating point binary numbers and vice versa. So we have this first number with its mantissa and exponent. If we look at the exponent, remembering that this is written in 2's complement, we have the positive value 3, which means we need to move the floating point 3 places to the right. So if we move that floating point 3 places to the right, we can then put in our place values. So as with the fixed point, but remembering this is in 2's complement, we have the fractional part to the right and the whole number to the left. Now if we add these numbers up, we've got 4 and 2 on the left hand side, that's our whole part of the number, 6, and then 1 over 2 is 0.5, so we should have 6.5. Here is another example. We have the exponent of positive 4, so again moving the floating point to the right, and if we move that 4 points to the right, we end up with these place values. If we add these up, we get 8 add 2 add 1, and then 1 over 8. If we add those together, we get 11.125. Now we've moved into a number that is represented using a positive mantissa, so a positive value, but a negative number for the exponent. So if we look at the exponent, we've got negative 8 add 4 add 2, which gives us negative 2. Because this is a negative number, we're going to move the floating point 2 places to the left. Now if you look at the mantissa, we don't actually have the spaces for this, so I'm just going to add these in. And then we're going to move that floating point 2 places to the left. And then because this is a positive number, we're going to backfill with zeros to maintain that positive sign. Okay, so at this point, we're free to put in our place values. And as before, we just need to add the numbers up. So here we have 0.203125. Now, throughout the AQA MART scheme, it states that you can represent your answers as fractions if you prefer. If you can't remember how to create these fractions, this essentially came from finding the lowest common denominator for these numbers, adding those up, which leads you into 13 over 64. Here we have a negative mantissa and positive exponent. So if we unpack that exponent, we get positive 3. Because this is a positive number, we're going to move the floating point 3 places to the right. So if we go ahead and move that, so we're now able to put in our place values. Now if we add up the numbers we've got, we need to remember that we are starting from negative 8. So anything that we add on moves us closer to 0. We don't treat the whole integer part separately from the fractional part. So if we start with negative 8 and we add 1, that gives us negative 7. And then from there, we're adding on 1 over 2 and 1 over 16. So negative mantissa, negative exponent. So here we have negative 2 again. So we're moving 2 places to the left. Now, because this is a negative mantissa, it's a negative number, we need to move that decimal point 2 places to the left, backfilling with 1s to maintain the negative sign. So there we have, moved back 2 places. We backfill with 1s, that maintains the negative sign. If we add these up, again, that principle of adding positive values to a negative number moves us closer to 0. We can also represent this number as a fraction. And here's how we derive that. So lowest common denominator is 64. Adding all those together gives us 53 over 64. Now we've got a negative number here, So we represent this negative number using this construct. So negative 64 over 64 is the same as saying negative 1. So this is representing this negative 1 here. So if we add those together, we end up with minus 11 over 64. So here we have method 2. Just a reminder of the structure of the mantissa, and the reason I'm bringing this up is that in method 2 we don't actually move the floating point. So here's an example. The exponent is positive 4, which would have meant that we move the decimal or the floating point to the right, but in method 2 we don't actually move it. So we put our place values in and then we add up our fractions in this case. I'm just showing the fractions here just to show you that this is a possibility. You don't have to use fractions. You could have 1 over 2 and 1 over 8 represented as just decimal base 10 numbers. That's fine. But if I add these two together, I get 5 over 8. And then what we do in this method is raise whatever we've added up to the base number 2. We multiply it by 2 to the power of the exponent. So this is just the same as saying 5 over 8 times 16. So if we actually carry that out, we get the value 10. Okay, next example, negative exponent this time. We just extract the exponent, leave the mantissa as it is, and just add up what we have. So in this case, we have 1 over 2, 1 over 4, 1 over 8. That is 7/8, and we times it by the base number 2 to the power of the exponent. In this case, we've got negative 2. Just an example of what you can do with this. If you have 2 to the power negative 2, this negative can be treated as 1 over. So we can actually turn this into 1 over 2 to the power 2. That negative essentially becomes that line, and you plus a 1 over it and you're left with 2 to the power 2. If you actually do this, this becomes 1 over 4, and then 1 over 4 is 0.25. So implementing that, we come up with the answer of 0.21875. Here we are using a negative mantissa and positive exponent. So extract the exponent, positive 2, add up what we have. So we've got negative 1, added 8, add a 16th. That is the same as saying negative 16 over 16, 2 over 16, 1 over 16. The reason that this exists, this negative 16 over 16, is because this is a way of representing negative 1 using the same lowest common denominator that we've used here. All we do is we place the same value, a negative form of the value that represents negative 1, so that we can actually use it in our fractions here. Again, you don't have to be using fractions. You can do this as a decimal number if you wanted to. So if we add those up, we get negative 13 over 16 times 2 to the exponent. That gives us 3.25, or we could write it as negative 13 over 4. Here we have both a negative mantissa and exponent. Now the exponent is negative 2. We'll come back to that in a minute, but we can add up our mantissa. So negative 1, add a quarter, add a 16th. If we take the next step, so this is representing our negative 1. We add this together, and that gives us negative 11 over 16 times 2 to the exponent, which was negative 2 in this case, and that gives us 0.171875. Again, we can represent it as a fraction. You don't have to, but that's what we would do, mentioning that technique I showed you earlier, where this negative sign becomes that, and this 2 falls down to here. It's always 1 over. Okay, and that would be our answer.